Rings and distributivity. Remember that Z with this special font is reserved for the set of integers, which includes all natural numbers 0, 1, 2, 3, 4, and their negatives, -1, -2, -3, -4, and so on. The main result of the first part of this lesson is that the set of integers, together with addition and multiplication, is a ring. So what is a ring? Well, a ring is a triple R plus times, where R is a set, and plus and times are binary operations on R, satisfying three properties, each of which consists of some subproperties. So let's look at each one in turn. The first big property is that R plus is a commutative group. Now remember that being a commutative group means that you satisfy a bunch of properties. Let's just review those. Closure. For all xy in R, x plus y is in R. Associativity. For all xy and z in R, x plus y plus z is equal to x plus y plus z. Commutativity. For all xy in R, x plus y is equal to y plus x. Identity. There exists an element 0 in R such that for all x in R, 0 plus x and x plus 0 are both equal to x. 0 is known as the additive identity element. Inverse. For each x in R, there is y in R such that x plus y and y plus x are both equal to the additive identity 0. We will usually write negative x for the additive inverse of x. So we have that x plus negative x and negative x plus x are both equal to 0. Second property is that R times is a monoid. So remember that being a monoid means the following. Closure. For all xy in R, x times y is in R. Associativity. For all xy and z in R, x times y times z is equal to x times y times z. Identity. There exists an element 1 in R such that for all x in R, 1 times x equals x times 1 is equal to x. 1 is called the multiplicative identity element. And the third property, multiplication, is distributive over addition in R. What this means is that for all x, y, z in R, x times y plus z is equal to x times y plus x times z, and y plus z times x is equal to y times x plus z times x. Note that we're using the usual order of operations here that we learned in elementary school, so multiplication will take precedence over addition. For example, when we have x times y plus x times z, we mean to multiply x and y and multiply x and z and then add the two. The property on the left here, the first distributive property, is known as left distributivity, and the second one is known as right distributivity. When we have both of them, we can simply say that the structure is distributive. Okay, so let's look at all these properties together. When we have all these properties, we say that this collection is the collection of ring axioms. An axiom is simply a statement that we're assuming to be true. So whenever we say that we have a ring, that means we're automatically assuming that all of these statements are true. These are called the ring axioms. There are other statements that are true in a ring, but those need to be proved. Some mathematicians do not include the identity axiom for multiplication in the definition for a ring. There are good arguments for both including and excluding this axiom. For our purposes, it's more natural to include it, so we will always include the multiplicative identity in the definition of a ring. Notice that the set of integers, together with addition and multiplication, satisfies all of these axioms. The set of integers, together with addition and multiplication, is a ring. Z plus times also satisfies commutativity for multiplication. So that property says that for all x, y, and r, x times y is equal to y times x. Since we have this additional property, we talk about a commutative ring. So the set of integers together with addition and multiplication is actually a commutative ring because it also satisfies commutativity for multiplication. Note that all rings satisfy commutativity for addition. If we also want commutativity for multiplication, then we need to call it a commutative ring. In a commutative ring, left distributivity implies right distributivity and vice versa. So we only need to list one of them. So usually we'll cross out right distributivity, and we can just leave left distributivity for the distributive property, because using that together with commutativity, it's pretty easy to prove that right distributivity also holds. The set of natural numbers together with addition and multiplication is not quite a ring because the set of natural numbers together with addition is not a group. In particular, the inverse property for addition fails. For example, the natural number 1 has no additive inverse in the set of natural numbers. In other words, the equation n plus 1 equals 0 has no solution in n. We say that the set of naturals together with addition and multiplication is a commutative semi-ring. So a commutative semi-ring satisfies all the ring properties except for the additive inverse property, and in place of that we put a different property called the zero property, which says for each x in R, 0 times x and x times 0 is equal to 0. Okay, so a semi-ring has this additional property. Note that rings also have this property. It's just not listed explicitly as an axiom, but it follows from the axioms. When we take away the inverse property for addition, we inadvertently take away this zero property as well, and we would like to include that in the definition of a semi-ring. The set of rationals, together with addition and multiplication, is also a commutative ring. In fact, Q plus times is a field. Okay, a field has the additional property of every non-zero element having a multiplicative inverse. So for all x in R, x non-zero, there is y in R such that x times y equals y times x equals 1. Note that we need to exclude 0 because 0 can never have a multiplicative inverse. Anything times 0 is always equal to 0 and not 1. Okay, there's one exception to this in the 0 ring where 0 and 1 happen to be equal, but that case is trivial. We do also include one extra technical property for a field, and that is that we insist that 0 is not equal to 1. In a ring, we allow the possibility for 0 to equal 1, in which case we just get what's called the zero ring, a ring consisting of just one element. But for technical reasons, we don't want to allow this possibility for a field, so we insist that 0 and 1 are distinct elements in a field.